In Chapter 2, we developed all the tools we need for computing the differential and the derivative of various algebraic functions and transcendental functions. Always in the back of our mind, remembering that the derivative, by its definition, can be thought of as the slope of the curve at any given point, as well as the instantaneous rate of change of a function. And it's that second interpretation of the derivative that we will use predominantly here in related rates. So in general, a related rate problem, we're given the rate of change of some quantity and we're asked to find the rate of change of another. In such problems, typically we'll use implicit differentiation as the calculus tool for solving the problem. Of course, it'll require us to use many other ideas from geometry and algebra to set up the problem, but implicit differentiation will be the calculus tool that typically will be the tool we use to solve the problem. Now, in the previous video, we talked about a mnemonic that I use whenever approaching a word problem, and using the mnemonic WORDS, which stands for wonder, organize, relate, determine, and solve. Now, wonder itself means to wonder about the problem. And I use another mnemonic, cube, to guide me in that wonder. And cube stands for circle, in which I circle key numbers and variables. U for underline, I will underline the question that's being asked. B for box, in which I box any math action words. And finally, eliminate, in which I eliminate any extraneous information that may be in the problem. And then I'll organize my thoughts using diagrams and assigning variables to the various quantities in the problem. I'll relate the variables and values via equations. I then determine an approach to use to try and solve the problem. And finally, I will solve using that approach and check my answer. And of course, the determine and solve may be a trial and error. Oftentimes there can be multiple ways to approach a problem. It's not clear from the onset which will lead to an answer, a correct answer. So that's why it's important, once you solve using that method, that the answer is checked. Do the values make sense? Is there another way can I double check and confirm that I have the right answer? So we could sit here and talk abstractly about related rate problems, but it really makes more sense to just jump in and look at an example. So the first problem we look at will be this question, in which we're told a point moves along a curve y equals square root of x in such a way that the y value is increasing at a rate of 2 meters per second. And the question here is, at what rate is the x value changing when x equals 4? So again, the first step is to wonder. So I circle any numbers and variables. So here is a whole bunch of variables. So y equals square root of x. Here is the y value. Here is a number, 2 meters per second. Another variable, x, and x equals 4. So these are our math numbers and variables. Let's underline the question so the question is quite clear. At what rate is the x value changing when x equals 4? There's our question. And then we'll box any math action words. Well, this one actually gives us equations. So these are clearly some actions. Y equals square root of x. That's a mathematical relationship. And of course, I want to know, here's another math action, x equals 4. Some other, though, is that it's increasing at a rate. This is a derivative, right? Increasing at a rate. So that tells us that we've got a derivative going on, and then at what rate? Again, that's a derivative. So we've got that, and there doesn't seem to be any extraneous information here. It's all very concise. So now we're going to organize our thoughts using diagrams. Well, the first should be, let's just draw the picture, the graph of y equals square root of x. So drawing its graph, y equals the square root of x. Its curve looks something like this. So that would be y equals square root of x. And so I've written that down as well. And we want to know what is so we're told the y value is increasing at a rate of 2 meters. So we can relate that dy is increasing at a rate of 2 meters per second. So I know its underlying variable, it's a function of time. So dy dt is equal to 2. And I'll go ahead and write our units so that we can check units at the end. So dy dt is equal to 2. And then we're asked in the question, what rate is x value changing when x equals 4? And this is going to be with respect to time. So the question here is, what is dx dt equal to? And it's got an evaluation, so when x equals 4. So we're going to evaluate this when x equals 4. And it's asking, what is that equal to? And if we wanted to even further, we could put on the graph here, maybe here is 4. And this here would be the point 4. And if we put 4 into the function, the output would be 2, because the square root of 4 is 2. So now I've organized all the data, all the information that's in here. Notice I've got everything that I've circled and squared, even the underlined. I've got everything in place. I've collected all my information. And we need to now relate all our variables. Well, in this problem, we already have a relationship, right? It was given to us. Oftentimes we'll have to discover it, but so now we will say that our underlying relationship is that y is equal to, and I'm going to write as x to the 1/2. So just because I know a priori, I'm going to take derivatives here, and I'd rather think of this as a power rule. Okay, so that's my my underlying relationship. Here's the problem I want to ask. What is dx dt? And I know that dy dt is equal to the constant 2. So this is constant all the time. And so what is my approach? Well, as I said earlier, these related rates problems, implicit differentiation is our go-to problem. And so since these are all related rates problems, that's going to be our approach. Now, later on when we have different problems, like we're going to optimize things and other approaches, then it won't be clear. We'll have to determine what are we trying to answer. But in this, because I know it's a related problem, I'm going to use my approach will be implicit differentiation. So my approach is implicit differentiation. All right, so this is what I'm going to use to solve the problem. So let's get to work then. So I've got this relationship, dy or y is equal to x to the 1/2. So I could differentiate both sides. This tells me that dy is equal to d of the function x to the 1/2, which is equal to 1/2 x to the negative 1/2 dx. All right, so we differentiated both sides. And now in implicit differentiation, we would solve for dy dx, and we would know that, oh, dy dx is equal to 1/2 x to the negative 1/2, which is no surprise. We know the derivative of the square root function. But in this problem, we know something about dy dt. We know something about dy dt, and we want to know something about dx dt. So it wouldn't make any sense to divide everything by dx. And you can do it, but the information we have is about dy dt, and the information we want to know is about dx dt. So the sensible thing would be to divide by dt. So I divide by dt, divide by dt, and I'll collect things so I get that dy dt is equal to 1/2 x to the minus 1/2 dx dt. Now we can use our information. Dy dt is equal to 2. Right? So now all we've done is come over here and taken what we know, that dy dt is equal to 2. And so we use that information right here, replacing, saying, oh, dy dt is equal to 2. And now I can solve for dx dt in this problem then. So this tells me that if I were to multiply both sides by 2 and then divide by x to the negative 1/2, I would get that 4 x to the 1/2 is equal to dx dt. Why do I want to solve for dt? Well, it comes back to, well, what's the question being asked? I want to know, what is dx dt equal to when x is equal to 4? And now I can put that together because I have an equation. Because dx dt when x equals 4 is equal to 4 times 4 to the 1/2, which is equal to, well, the square root of 4 is 2, so this is equal to 8. And now I need to put my units in here, but the units for this 2 were meters per second, and that's the only value with units we have, so this will be meters per second. And that's our answer. Our answer is that when x equals 4, the rate at which the x value is changing is 8 meters per second. Now, on homework or in an exam, I would ask that you write your answer out in a complete sentence. Because it's so slow and tedious for me to write it out here, I'm going to verbalize the answer. But again, what I would be looking for in an exam is that your final answer would be something like, the x value is changing or increasing at a rate of 8 meters per second when x equals 4. But again, I don't want to bore you with me writing that all out, so I'll say it verbally, but remember that you will want to write your answers in complete sentences.